I realized that maybe we're on the same wavelength even more than I thought. Well, we'll see.
I hope so, but maybe not. I don't know. So in any case, we'll have fun. All right. Thank you. This book was kind of a labor of love, as I was explaining. It wasn't sort of directly related to what I do or have done for a living, but is a subject I've always been fascinated by. And the more I delved into the history in particular, that became a bigger part of the book, and to me it was very interesting. And I'm a big believer that to really understand something thoroughly, you have to sort of understand how it evolved, what its history was. And I believe that even more firmly now, having gone through this experience. Like anything, at a certain point you have to sort of push it out into the world and just sort of say that it's completed, and I did that, a couple of years ago. And I haven't spent a lot of time sort of thinking about it since, but when Glenn mentioned the possibility of coming here and talking about this, I started thinking some more about a few of the kind of loose ends of the book that had always sort of bothered me, that maybe I hadn't quite explained it as fully or as well as I thought I could. So in that spirit, I've kind of thought about a couple of issues I'd like to talk about that are talked about in the book, but I think sort of take off from that discussion and see if I can kind of push it a little bit further. So the book is called Willful Ignorance, the Mismeasure of Uncertainty. And when I say the mismeasure of uncertainty, it's because what I sort of learned in the part of this historical excavation that I was doing was that our notion of probability, the one that's sort of second nature to us all, we all grew up with, is a historical event, historical construct, and that it comes out of other ideas about uncertainty that existed before probability as we know it existed. And so I came in the first chapter, which I rewrote sort of long after I had gotten through other chapters, and I call it the opposite of certainty, because thanks to Jacob Bernoulli and some of the other, and John Maynard Keynes and a few, and Ronald Fisher, who's my intellectual hero, and I'll talk more about him later on. It is clear that prior to the 1700s, at least, and well into the 1700s, our idea of probability really didn't exist as such, and there was a sort of an earlier notion of probability that it's probably kind of more akin to belief theory, as my limited understanding of it, at the work that Glenn has done, in which probability had a much broader sense. And I summarize this by talking about the notion of ambiguity and doubt, two different aspects of uncertainty, and that our type of probability deals only with what I would call doubt. In other words, we put a probability on a scale from 0 to 1, and 0 represents basically impossibility, and 1 represents certainty. And it's where you sit along that spectrum. That's what we call a probability. And in Jacob Bernoulli's understanding of things, it didn't work like that. It worked like if you had a 0 probability, that means you had no evidence, no information to base your conclusion on. And if you had built that up towards 1, that meant that you had more and more evidence. It was how you built an argument, basically, in favor of something. And what that meant was that rather than, if you think of the glass half empty and the glass half full, we think of the full part as being our idea about whether the event did occur, and our empty part is the probability that it did not occur. In their view, you could have a 90% probability that it did occur based on the evidence, and you could also have, let's say, a 70% probability that it didn't occur. But of course, those would be based on different conceptions of the problem, and that's where the ambiguity aspect comes in. It's how you conceptualize the problem. So one example I like to use is if you had somebody evaluating a person in a trial for their competence, let's say, and they were a Freudian psychologist, a strict Freudian psychologist, and they were looking at the person's childhood and the traumatic events that occurred in it and their relationship with their family members, etc. And then you had a strict behaviorist who didn't care about any of that stuff and was just looking at sort of various incentives and responses that they had throughout their life. They might come to very different conclusions, and you couldn't even put them on the same scale, so that the idea of a total evidence that would encompass them both might really not be realistic at all. Okay, so you had this idea of sort of two very different tracks on which the probability was being built. And John Maynard Keynes, for example, had very much the same idea in his book on probability in 1920, that was published in 1921, where he saw probability being on different tracks so that they weren't commensurable with each other. So from that sort of idea, at least as expressed by Jacob Bernoulli, and Bernoulli then came up with this novel idea that, well, suppose we had a situation where we could sort of ignore that. Well, actually, I won't go into that. There's more discussion about that in the book, and I won't go into that in detail. I want to talk about our probability. That was just sort of by way of background. Our probability, where you have basically a measure of your doubtfulness or your lack of doubtfulness about something is that probability. And the sense that I had for a long time tried to understand, as I'm sure many of you had, what is that probability? Is it subjective? Is it objective? Is it a long-run frequency, et cetera? And I sort of came independently to the conclusion that probability really is a way of thinking about things that draws an analogy between how much certainty you have and a lottery or a game of chance. I call it a metaphorical lottery. And in the book, I talk about Fisher a lot. And since Fisher said it much better than I can say it, I'll quote him, if you'll forgive me. He says, probability statements do not imply the existence of a population in the real world. All that they assert is that the exact nature and degree of our uncertainty is just as if we knew it to have been chosen at random from such a population. The subject of a probability statement, if we know what we are talking about, is singular and unique. We have some degree of uncertainty about its value, and it so happens that we can specify the exact nature and extent of our uncertainty by means of the concept of mathematical probability as developed by the great mathematicians of the 17th century, Fermat, Pascal, Leibniz, Bernoulli, etc. So Fisher said, and this was kind of a revelation to me because I had sort of come to the same conclusion, and here was Fisher saying exactly that. Often I found that when you read Fisher, originally you think that what he says makes no sense or is inscrutable, and then later on when you figure it out yourself and you read it, you say, aha, so that's what he was talking about. And that's R.A. Fisher. That's my experience anyway. So I talk about probability as being a metaphorical lottery. What do I mean by that? Do I mean that it's actually a physical lottery? No, I mean exactly what Fisher was talking about. And the source of that metaphor could be anything. It could be a real situation in which you actually are looking at a lottery. And I'll give some examples with simple card tricks that will illustrate some points that I want to make. Or it could just be your intuitive feeling about what is the degree of evidence, what number between 0 and 1 would specify your uncertainty. So in essence, this lottery can be thought of as a very simple lottery. Jacob Bernoulli talked about a series of tickets in an actual lottery where you looked at it, and that this was a conceptual. It was clear that Bernoulli meant it as a conceptual thing, not a real thing, and that this was an idealized lottery, not an actual lottery that you would be participating in. And so in the end, or ultimately, you could reduce any lottery to a very simple lottery conceptually in your mind. But the lottery itself could also be something that's pretty complex. It could involve a series of steps and procedures, some of which are probabilistic, some of which are deterministic in some complex way. And that is what I think Glenn calls a protocol. Am I right about that? Okay. And this notion of a protocol, unfortunately, and I want to publicly apologize to Glenn because I came upon the protocol idea fairly late in the game of writing the book, and I wasn't aware that in 1985 he had written a book on an article on conditional probability that basically introduced the term protocol. So thank you, Glenn. I love it because it sort of gives you the idea of what it is. It's a recipe, essentially, for how exactly you're going to carry out some set of procedures. And it turns out that the probability in such a complex lottery may not at all be obvious. It may be quite confusing. And the reason for that is primarily because it hasn't been defined unambiguously. And I'm going to give some examples of that. Okay, so in principle, and it may seem like just an abstract concept, a theoretical concept, you need to know what protocol you're talking about if you want to make sense out of a probability. Just as a sideline, and I'll talk a little bit more about it later, I think in science, this is really a very important notion because a scientific experiment is really the execution of a protocol, and it's very important to know exactly what that protocol was. One of the things that statistics as a profession, and personally that I'm involved in today, is dealing with these so-called big data situations, data science, where you have potentially a very complex situation involving many studies on many different variables, sometimes thousands or even millions of, quote, variables, namely genetic variables or genomic variables, proteomic variables. And so that the experiments you're carrying out could be extremely complicated and have implicit protocols within them. And statistics as a field was developed at a time when that didn't exist and when the amount of data and the types of studies that were being done were very simple, really. And so when Fisher and Neyman and the others were grappling with these problems, they came up with the fundamental concepts, but they didn't have to deal with the idea of having many multiple studies or sequences of studies or studies that get published in journals and some get published and some don't. These are essentially protocols that we deal with, but nobody, not want to say nobody, but they're not really dealt with explicitly. And so the idea of a protocol, I think, has really important implications in science today. But from the ridiculous to the sublime, or vice versa, a couple of examples of protocols, because I want to use these later on to illustrate a couple of important points, I think. So I have here 4 cards. And this is one that Glenn mentioned in his article. It's called the 2 aces problem. Is this something familiar to people? 2 aces problem? Some of you have heard of it before? Okay. So I have an ace of hearts and an ace of spades, a 2 of hearts and a 2 of spades. And I shuffle them up. And then I deal a hand. Okay, and look at it. And first thing I say, let's try again. Let me try again. This is all right. So let's deal a hand. Okay, and I look at the hand and I say, I have an ace. Okay. Now, then the question is, well, what's the probability that I have both aces in this hand, right? And a little bit of elementary probability will tell you that there are 6 possible hands that can be dealt. Only one of these, the one that has 2 deuces, will not have an ace, right? So by the usual rules of probability, you would say it's 1/5 is the probability that I would have both aces, okay? Because that only occurs one time. Okay. Now, and suppose now that instead of that, I had told you I have the ace of hearts, okay? What would be the probability then that I have both aces? Okay, anybody? What's that?
1/3.
1/3, right? Because with the ace of hearts, I could have any of the other 3 cards, and they're equally likely to be part of the hand. So it's either 1/3 or 1/5. So, and there are many other ways, of types of protocols in terms of when would I say certain things and when wouldn't I, depending on what I actually have in my hand and what I've seen. And so the protocol is very important in terms of defining what the probability is. In this one, the paradox is supposedly that if I would say it's 1/3 if it was the ace of hearts, if it happened to be, if I said the ace of spades, you would also say 1/3. And so if it's 1/3 either way, why is it 1/5 when I don't know, when I just say that I have an ace? Okay. It's not really a paradox, but and it seems to change when I tell you which ace I have. But I could have had a different protocol. I could have said, let's suppose that when I picked up the hand, I looked at it quickly and I really only looked at the first card and I said, oh, I have an ace. But I've only looked at the first card, right? Once again, what would the probability be in that case? Be 1/3, right? Because I've only looked at one card and the other three are equally likely to be the other cards. I could have had the ace of hearts, and the other ace, or I could have had the ace of cards and then one of the other two cards. So these seem like, well, they're paradoxes. They're really not. They're just a matter of not being exactly clear on what the protocol is that's being talked about, even in a very simple situation like this. Okay? Questions?
Is that like the Monty Hall problem?
It is, and my next thing is going to be the Monty Hall problem. That's very good. I didn't tell him to say that. Yeah.
Can you just one more time give your intuitive gloss on what a protocol is in general terms?
Okay. So a protocol would be a complete statement of what procedures and what information has been revealed at each step of a process. Basically, is that pretty good? Or you could probably do better, but that's off the top of my head. So in the first case, when I told you I picked two cards and I had an ace, my protocol there would be dealt two cards randomly from out of the four. If I have one or more or both aces, say that I have an ace, and if not, I wouldn't say it. And that's what happened the first time, which is why I did it the second time, because I had two deuces, which was annoying. So I could have faked it, but I decided not to. And then that's basically it. And as long as you spell out completely what it is that is the procedure that you're looking at. The Monty Hall problem, which is probably one that's the most famous, shows a little more clearly, I think, the role of the protocol. So in the Monty Hall problem, I guess I'll read the description just so I don't get it wrong. If you'll bear with me for a second here. Okay. I guess I can't because I can't find it, right? There we go. Okay, so the Monty Hall problem, which created a big stir when it was in a magazine, it was expressed in the following way, and readers wrote in and they were all over the place in terms of what their answers were. It says, suppose you're on a game show and you're given the choice of 3 doors. Behind door 1 is a car. That's the prize that you'll win if you can find it. Behind the other are goats. You pick a door, say door 1, number 1, and the door is not opened. And the host, Monty Hall, in the case of the actual TV game, he knew what was behind the doors. He opens another door, say door 3, which has a goat, as it happens, and he says to you, do you want to pick door number 2? Is it to your advantage to switch or not to switch? Okay, so let's sort of simulate that with our cards here. And by the way, this is sort of in honor of Monty. He passed away last week at the age of 93. I read that, so the actual Monty Hall. So let's suppose that this ace of hearts represents the car, and these two deuces represent the goats, okay? And so I'm going to shuffle them up. It's hard to shuffle 3 cards. I'm doing the best I can. All right, and this will be door 1, door 2, and door 3. Okay? Let's see. And now, this is your original choice. Okay? And now you're asked, should you switch? You have the option of switching to either of the other doors. But Monty, who knows what's under these doors, okay, and let me see if this, okay. All right, so Monty shows you this one and says, aha, okay, I've given you a clue. This is a goat, right? So what do you think now? Okay, well, the first answer was people would come up with is, well, it's got to be a half, right? Because there are only 2 left, and we know they were all equally likely to be the car to begin with, so why isn't it a half? And the real answer is that, what is the real answer? For those of you who know the Monty Hall problem. Somebody? You switch because, and why do you switch? Okay, well, if in fact I had picked this randomly, then switching would be fine. Or if I knew ahead of time what it was, and I just picked, I said I'm going to pick door number 2, and that's going to be it before the game, then that logic would be fine. But in this case, Monty, the tricky fellow that he was, would know what was behind the door, and he would never show the car if it was there. Okay, so in this particular game, the car is right here, and so Monty picked this one. So in fact, the probability of winning would be 1/3 if you stuck with your original choice, but it would be 2/3 because regardless of which one of these was the one that had the car, that's not the one you would be seeing, you'd be seeing the other one. Okay, so the protocol, if that was the protocol, and that was apparently what the real protocol was, the protocol was, you know, offer them to switch, turn over the one that didn't show the car, or if they were both not showing the car, then you could do either one, and then you know, offer them the choice. And under that protocol, it's 2/3. Now, something to me that's always been a little bit uncomfortable about that, which is that, you know, beforehand, I knew that the probability of this card, let's say, was 1/3. Well, why is it now 2/3? In what sense is it 2/3? Okay, and I'm going to talk about that a little bit later.
Answer, why is it 2/3 again?
Yeah, why is it 2/3?
I'm not 100%
Oh, okay.
sure either, yeah.
Because, well, one way to think about it is if it's, okay, you know, if I play this game over and over again under exactly that same protocol, then in 2 out of 3 times the car will be in one of these 2 places. And I know that if I switch, I will get the car regardless of which one it's in, because Monty will only show me the goat. Okay? So if I play the game over and over again, then 2/3 of the time. Now, and this is an important point, in this particular game, it's certainly possible that the ace was here and that there were 2 goats here, in which case, of course, you would win. But as a long-run frequency type of probability, you'll 2/3 of the time you'll win by switching. So you should always switch from that point of view. Okay?
But your point is that the probability is highly dependent on the protocol.
Of course, yes.
The protocol was the fact that you knew, but if you didn't know, that's a different.
Yes, exactly. It depends on the protocol, right? It's not just, and so confusion about the protocol means that you'll be confused about the probability. Okay? Now, here's the one that gets a little bit hairy. Okay. This is called the 2-envelope problem. How many of you are familiar with it? You're familiar with it, right? The 2-envelope problem? Oh, well, okay. It's a great problem. And I'll do it this way. I need 2 envelopes, obviously. Here we go, 2 envelopes. Okay, 2-envelope problem is this. You're playing a game, and you're told that there's a prize in each of these, you know, a check written for an amount of money in each of these envelopes, okay? And the only thing you know is that one of them is exactly twice the other one, okay? One of the prizes is twice the other prize. So I give you you look at the 2. You can get to choose whichever one you want, okay? So pick one of these. Pick one.
This one.
This one, okay. So you pick the envelope. And now I show you the amount that's in the envelope. Let's see, in this case, okay, it's $2,000. All right, now I say, well, do you want to switch to this envelope, or would you keep your prize? So, any takers on this for?
Switch and then switch back. Okay.
Switch and then switch back, exactly. Good. You know, see, you've heard this before. I know you have. See, okay, all right. So the argument is this. Well, on the one hand, these were put in here before. I showed you these 2 envelopes. If this is, whichever you do, you're either going to gain or lose something, right? Depending on what this is. And then if you did it back again, you gain it. But the counter, so there really shouldn't make any difference which one you choose. I mean, you didn't know anything beforehand. All you know is that's 2,000. You don't know why I picked 2,000 or what's in the other envelope. But the other argument is, well, this is 2,000, and this has got to be either twice or half, right? So it might be 4,000, and it might be 1,000. You don't know which it is, okay? So why shouldn't you switch? Because you have a chance of going up by 2,000 and only going down by 1,000, so your expected value is going to be higher, according to that logic. But again, what's wrong with that? Because if this is 4,000, but you didn't know that, and you picked this one, you would switch back to this one. What's going on here, right? It sounds very
You're allowed
strange.
to switch back after you make this?
Well, not now because you've seen it. I mean, but if you hadn't seen it, if you did it before and you said, okay, well, I'll switch to this, and then you could switch back again. But I could have shown you this one, and you don't know whether this is higher or lower, but it's the same thing. You would then switch to this. Well, that can't be right. I mean, in the long run, you know, you're not going. You can't benefit somehow in this game. It doesn't seem like. And yet, the logic of it might be, well, but logically, I know that this has got to be either 4,000 or 1,000, and so why wouldn't I? Okay. So just hold that kind of thought. I'm going to try to explain that later on in a little bit better way. There are many explanations that have been given, and one explanation way of explaining it is say it depends on the protocol, okay? That's one way you could think about it. I mean, if I knew, for example, I was a Bayesian and said I knew the distribution of prizes from which I picked these prizes, right? And I knew that, let's say I could know that I would never give a prize more than $2,000. Well, if I knew that information, then I would know for sure that this must be $1,000, and so I would know that I better switch. So it could depend on what you assume about the prior probabilities of getting different amounts in the envelope, okay? That's one way that people think about it. It depends on that protocol. You have to specify exactly what the protocol is. If there's ambiguity about the protocol, then you run into these kind of logic problems. I think there's a deeper issue here, and I want to talk about it later, okay? But that's sort of the starters, the two envelope problem. It's mystified a lot of people. All right, so going back, now I want to talk about another concept here, which is that, and this helps, I think, to explain some of these things.
Sorry.
Yeah, go ahead.
So when are you given the choice to switch?
Good point. In this case, I said that you are given both of the envelopes, and then you can choose one or the other. Now, another way that this game could be played, another possible protocol would be, and this would be like on a computer, for example, where I could show you one envelope, I don't show you the other one, and then ask you, and then based on, after you look at it, I pick one or the other of the higher or lower at that point. Then this protocol would correspond exactly to the idea that you should always switch, right? Because your expected value would actually be higher. Your physical objective value would be higher. Okay? So you can, if you want to read about this, there's lots of people have had lots of opinions about this thing. Okay. We'll get back to it later on. All right. So one of the things that comes up in these types of puzzles is the idea of conditioning on information, conditional probability, because in the protocols, and in these games at least, at some stage you're getting some information that may or may not be relevant to your probability assessments, right? Now, if you're doing a Bayesian context, I think of the Bayes theory as being a protocol, basically. It's a simple protocol. It says I have a probability distribution. I'm picking something out of that probability distribution. Then I'm going to have a conditional probability based on that value. And now I'm going to say, after looking at the thing I can observe, what does that tell me about the probability of the event? And Bayes' theorem is just a way of calculating that conditional probability. Okay, so based on information that you're getting, you can do that. But you have to have a prior probability in order to do that, right? Okay. So, put that aside for the moment. Okay, now I'm going to ask you another. I'm going to get a coin here. I have a quarter. Okay. This is going to be very simple. Okay, I'm just going to toss this coin. All right, and I'm going to say, and I'm going to allege that it's a fair coin, all right, and say, what's the probability that it's heads? You're all going to say, you think I'm trying to trick you, don't you? It's a half, right? It's a half, okay. But now, suppose I say, you know, I'm willing to bet you 3-to-1 odds that it's tails, right? would you take the bet? And if not, why not?
Did you look at it?
Well, that's one of the issues, right? And let's say I just say, no, I didn't look at it. What else would you be saying? You want to know if it's a fair coin, maybe, or if I tossed it in a certain way, or, right? There's all kinds of information that you might want. But suppose I told you that it's absolutely not, I didn't do any of those things, or at least I'm attesting that I did none of those things. So what would be the probability? That it would be heads. Still be a half, right? But what's different about those situations? This is going to be one of the main points of my talk, all right? What's different is that before I tossed the coin, there was an objective physical reason why it was a half, right? Because it was prior to tossing the coin, and we all know about tossing coins, right? After I put my hand over it, it was a done deal. Whatever it is, it is. There is no objective probability anymore. There's just uncertainty. You have uncertainty. You don't know whether it's a head or not. But why is it still a half? That's a different probability. It's now a subjective probability. And what you told me was, I think, was that, well, as long as I don't have any other information about this process, about this protocol that I just did, I'll stick with a half, right? So that's a principle. I mean, you don't have to do that, but it's a logical way of going about doing things. All right, we all agree? Okay. Okay, it's a tails. Look at that. Okay, so, all right. So the same thing applies in all these other cases as well. In the Monty Hall problem, again, the objective part of the equation is that there was a probability of 1/3 of being in each of those three places, or, whatever. But after I show you the one goat, there's a goat, okay. Now, it's not an objective probability anymore, it's a subjective probability, right? Because it's either here or it's here, but it's done. The deal is done. So now I've switched from an objective probability to a subjective probability. But in this case, I'm saying that this fact that this was a goat is totally irrelevant information under this protocol, all right? It could have been relevant if, in fact, another protocol existed, right, in which he picked this at random. But then it would have been more complicated because it's possible he would have shown you a car under that protocol, and he just didn't happen to. But in this case, we know that he would never have shown you a car, and therefore under this protocol, the probability becomes 2/3 for this guy. But the reason why it's not a paradox is because this is a subjective probability. It's not an objective probability in this game. It is an objective probability in a sequence of games. If you play this over and over again, this game, it would 2/3 of the time it would come out this way. But in terms of this game, it's either here or it's here. That end of story. There is no objective probability anymore.
If determinism were true, would that spoil your reason?
Ooh. Say what you mean, because maybe, I don't know.
Well, if determinism was true, there was something before you did the coin flip. Those facts in the world, together with the laws that tell how the coin would land.
Okay, fair enough. I guess that's true of an actual situation. I'm assuming that the analogy of this situation to an idealized lottery is valid, and that's an assumption basically that it's not deterministic, that it's probabilistic, as if I had a perfect lottery and I was picking these, or a perfect shuffling in this case, or something like that. Is that? I'm not sure that answers the question, but anyway.
I mean, it's a big issue because you might might think that determinism and there being probabilities are compatible with each other.
Yeah, I think the other way that I would think about it would be to say that, okay, maybe physically there is determinism, but let's think of objective as being, again, you're the philosophers, you know more about it. I'm using the term objective a little bit loosely here, okay? Objective means we would kind of all agree based on the physical setup. That's about the best I can do off the top of my head. That's what I mean by objective. There's something different about after the fact versus before I flip it. That's all I'm saying, really. Okay, if you So,
Yeah, the knowledge of how it fell is easy to obtain afterwards. Very
Yes.
difficult to obtain before.
thank you. That's a good way to put it. Okay, so, all right, now what about this problem? Okay, this is a tougher one. Okay, so what happens here, the way I think about it now, is this, that if you, once I pick these two numbers, however I pick them, and you know, I don't know how they were picked, and that's the point. I'm completely ignorant about how they were picked. So whatever I learn about the value of one of these or the other doesn't really give me any information because I didn't know what to expect beforehand. Okay? So in this case, it's true that once they're fixed, you know, you can switch to this one and then you can switch back to that one. You're playing only with two numbers. That's all you're playing with. However, in my subjective world, I know that if I saw 2,000, it has to be logically either 4,000 or 1,000. I know this for a fact. Now, why should I assume that those probabilities are equal? Well, I would say it's for the same reason that I gave with the coin or with any or the Monty Hall. It may be a good reason, it may be a bad reason, but what I'm saying is that since I don't, if the event that I'm interested in is, do I have the higher one or the lower one? That's an event, right? And I don't know beforehand whether I'm going to pick the higher one or the lower one. I know there's a 50-50 chance that I'll pick the higher one or the lower one, right? So therefore, is it logical to say, well, there's a 50-50 chance that it would be higher or lower in this case, okay? Well, what does that mean? In this case, it doesn't matter because the game is basically done. Okay, it's one or the other. But if I play this game over and over again and I want to bet on whether I have the higher or the lower, I think that's a perfectly reasonable thing to do, right? Why? Because knowing the value of $2,000 doesn't change my probability before I did the experiment that I'm going to be looking at the higher of the two, higher or lower. So if I played this game over and over again, and regardless of what I saw when I revealed one of the envelopes, I'm telling you that as long as this is completely random, and as long as I don't know anything else about the game, it's not irrational to just assume that the other one is going to have a 50-50 chance of being the higher or the lower. Now, all right. I don't know if you agree with me or if I agree with me, but I'm just putting that out there. Yeah.
Sorry, can you just restate what the conclusion is? Were you trying to support the idea that you shouldn't use switch?
No, I'm not, because what I'm saying is that it's a matter of keeping the quote objective part of it from the quote subjective part of it, okay? The before the fact objective part is the only probabilistic part of that is which one you choose, which has a 50-50 chance of being the higher one or the lower one, whatever they may be, right? That's the objective part. But once it's done, there is no possibility that this could be anything different than what it is. But I don't know that. I don't know what it is. All I know is that it might be higher and be $4,000, or it might be lower and be $1,000. That's all I know, right? And I knew that going in. What I knew going in was whatever I see, I know that the other one may be, that I may be looking at the higher one or the lower one. That's all I know. I may be looking at the higher one or the lower one, but logically that translates into, so that this becomes true as a subjective probability. It's not suitable for anything you would do within this game, but it is suitable if you have to make a bet at this point on is this higher or lower, right?
Wait, so are you,
it's sort of like Monty Hall.
So you're kind of not taking a stance on what you should do.
Oh, I am taking a stance.
So what should you do?
In this game,
Yeah.
it doesn't matter. You can't improve your situation in the long run by changing or not changing. Either one works the same.
Okay, so it's permissive.
Yes.
Okay.
But in this, I'm talking about a little different event, and that event, subjectively now, I believe that this is equally likely to be this one or this one. I believe that, and I believe in a long run of games of this kind, I'll find that half the time it's higher and half the time it's lower. That's what I believe. Okay. Okay.
You'd have an advantage if you picked some even without probabilities. prior probabilities, if you pick some threshold
Yes.
to decide to switch or not.
Thank you.
on that.
Yes, this assumes no information about that. If there's some, and of course in a practical sense, there's always a limit, right? I mean, it's not infinite money. So it's like I said, if it turns out that this is near the top border of where your possibilities are, then that would change your probability. Or if I had a prior probability distribution, that would change my probability. But it's the fact that I don't have that, and that this becomes irrelevant information. The actual amount becomes irrelevant. Okay? This is a hard concept, and I'm not sure I believe it 100% myself, but I'm putting this out there. And I'll tell you why, because you'll see that there's some implications of this. Yeah.
Right, so I agree that half the time it's higher and half the time it's lower, but when you say you're better off in the long run, you're going off of...
No.
You end up,
I'm not saying...
you're equally as well off.
No. Okay. I'm not saying... it's a different question. I'm not saying you're more likely to win the game that you're playing. What I am saying is that let's play a different game where I have to make a bet on which one, whether it's higher or lower.
So all you care about is higher or lower, not the monetary values.
Well, yeah, I'm not betting on the monetary value anymore. I'm just betting on the fact of whether the other envelope is either higher or lower. Okay, I'm just betting on that fact. Okay. And half the time it'll be higher and half the time it'll be lower. I mean... Okay, all right. So all right. So why is this useful? Well, we'll see. Okay. Now, to the real world. Okay. Okay. One of the problems that I've worked on is in clinical trials now. Suppose we're doing a trial between two drugs, right, to cure some disease, and we are trying to find out which one has a higher probability of curing the disease, okay? And the way that, and again, it's sort of a play on words, the protocol for a clinical trial specifies exactly how it's going to be carried out, and usually that involves randomization, where you're going to randomize the person to a treatment group or control group, let's say, or a treatment you're interested in some control, and then you're going to look at the outcomes for all those people, and you're going to compare them and see how they do, right? So, for example, here's an example. If this is a treatment group over here, and I'm going to assume that a red card represents a cure, and a black card represents a non-cure, okay? And I'm going to say this represents the population if they're treated. Now, this gets into the idea now, which is becoming popular, of a potential outcome. Familiar with the idea of a potential outcome? Glenn is, I'm sure, right? Which means that you hypothesize that for an individual, they would have one outcome if they were given this treatment condition, and they would have another outcome potentially if they were given the control condition, all right? And ideally, for each individual, you'd like to know for them what they were for an individual basis, but you can't know that. You can only know one of them because that's the condition that you're in, except if you have a crossover study or something. I mean, in some cases you can. All right, so suppose I deal, this treatment is not doing well at all. Oh, I didn't shuffle these, that's why. Sorry about that. I was supposed to shuffle them. That wasn't randomization, that was not good, not a good randomization, okay. So I'm going to randomize these, and I'm going to pick people for the study out of this population. What's going on here? I don't know how to shuffle, obviously. Okay, let's try it again. There, that's better. I got to learn how to shuffle. All right, let's see what we got here. Yep, I can believe this. This is, I should be doing card tricks. I can't shuffle. All right. All right, here we go. That's shuffle. All right. Look, this treatment is no good. Okay, so let's say there were 5 people here. Okay, and now we're going to do the controls. All right. All right. All right. The controls. Ooh, that's bad. Look at that. terrible. So the controls, none of them got cured, and the treatment, 3 of them got cured. So the traditional way would be to say, and assuming we had much larger samples, of course, that you had a 60% chance of being cured if you're in the treatment group, but only a 0% chance of being cured if you're in the control group, right? Okay, so that's the usual way of doing clinical trial studies. One of the things people are trying to do is to see if they can identify individuals who may be more or less likely to have a positive effect in the treatment, right? Because if you have certain genes, let's say, or maybe certain other biomarkers, we would call them in general, things about blood pressure or about some lab test that can be predictive of whether the treatment will work for you well or not, then that's what we're trying to find out so that we can individualize the treatment more to your particular characteristics, okay? This is called personalized medicine or precision medicine, it's sometimes called. So let's talk a little bit about the problem here. Okay, so here's, let's suppose that the treatment is not successful for this individual. Okay, we don't know what would have happened if they had gotten the control thing. Ideally, for each individual, if we knew that, we could see how many people improve or do better on the treatment, how many people do worse on the treatment, how many people, let's say, stay the same, okay? And so how might we try to get at some sort of an individualized type of a model that could tell us to predict whether the treatment would work or not? Well, one approach that's sort of simple and has some problems would be to say, let's suppose in each of these groups, we look at the data again that we had before, whatever it was, and we just do a model to predict whether they are cured or not, okay? And there's a technique called logistic regression. Are you familiar with logistic regression, everybody, or not? Logistic regression, okay. Well, it's a statistical technique, very commonly used in that sort of situation. It says if I knew for each individual a value of whether or not their event occurred, and usually it's coded as a 1-0 event, and then I know a characteristic of them that I'm interested in, or a set of characteristics, just like a regression analysis, I can develop a model that will estimate the probability of success based on their characteristics. Okay, so that's a very common thing to do. So what you might think of doing is saying, well, let's build a model for the treatment people, and then we'll build a model for the control people, and we'll say, okay, so if I know that, and let's say it's blood pressure, that's the thing that's very predictive, that if I could measure their blood pressure, then I could use this model to estimate their whether or not probability of being cured, and then I could use this model to estimate the probability of being cured under the control condition. Okay, so what's wrong with that? Anybody tell me, get some idea what might be wrong with that? No takers. Well, there's nothing wrong with it per se if I knew which variable was the one that I was interested in. But in a lot of these studies, there may be hundreds, even thousands, if you're talking about genomic, or hundreds of thousands of different variables that might be of interest, and you don't know which ones are the ones that are really going to be predictive on an individual basis. So that's the conundrum that exists in the real world in doing clinical trials. Well, here's a method that I developed, but other people sort of came upon this idea too independently as a kind of an interesting way to do it, and it ties into what I think I've been talking about here. Okay, it says this. Okay, so suppose that I look at this individual and they're cured. Great. Okay, I don't know though what. I don't know what would have happened if they weren't cured. So there's two possibilities. Either they would be cured under this one, or in which case it's a wash, or maybe they wouldn't have been cured under this one, in which case we would say that the cure was apparently was because of the treatment, at least in this simple case. Okay? So that's one possibility. And in this case, let's suppose that the opposite happened, okay, where in this case I have a control and they were not cured. Well, again, you can go the other way and say, well, it's possible that they would have been cured under the treatment, we don't know that, or it's possible that they would have not been cured, in which case, again, there would be no improvement. But what's interesting here is that in either case, you're getting a sort of a partial indication that the treatment has been successful. Okay, this is sort of what you'd expect to happen. If the treatment's good, then the fact that it's worked here, if the treatment's better than control, the fact that it worked here and it didn't work here is both kind of evidence in that direction. And conversely, it would work the other way around if it was like this. If the treatment was a failure, or the control was a success, that would work the other way. That would say, oh, well, maybe the control is better than the treatment, all right? So what we're doing is now saying, well, that's true after you know what treatment they received. But suppose I pretended that I didn't know what treatment they received, okay? That my information was not this. Let's take a different protocol, not the usual one that we use. But the protocol is going to be this. If this occurs or this occurs, I'm going to report that something happened, that an event, which I'll just designate as whatever, Z, that Z happened. If this or this occurs, I'll say it didn't happen. Okay, now I have an indicator that is in some strange way kind of related to whether the treatment is effective or not. Because these two things are sort of consistent with the idea that it might be effective. These two are kind of consistent with the idea that it might not be effective, okay? Well, it turns out that with very little bit of algebra, you can show that the probability of that event happens to be the difference between the probabilities of the two, of being cured under the treatment versus probability of being cured under the control. It's not hard to show. So what that means is that now I can use logistic regression on this transformed variable, and I can find variables that are predictive using that. It's a transformed outcome variable. And it works because we've done it. And you can try different ways, different variables, and see which ones seem to be predictive, okay? And the advantage of this is that those variables are directly predicting the thing you're interested in, which is the difference between the probabilities. It's very much like what I talked about before, though. It's saying, well, yeah, but you know that this one got the treatment, you know? I mean, why should I ignore that information? The point is that information is really irrelevant. The information of which treatment they got is irrelevant to this variable's value. So it doesn't matter. I might as well ignore that information. Whether I know it or not, I'm going to ignore it, okay? It's a different protocol for looking at the data. And so that's an actual application kind of this sort of idea, okay?
If you had a person duplicator, you could bypass all this.
If I had a person duplicator, I could, yeah. Then I wouldn't need to do this, but I don't. Or if there are some situations where you know that, let's say, the treatment doesn't carry over to the control, so you can, you know, first give them this treatment and then give them this treatment. That's a pretty good way of doing it, but that doesn't work in a lot of situations, most situations. Before I go on to my last, yeah.
So that's the, you talk about a crossover design kind of experiment, right?
Yeah, it's like a pseudo crossover, yeah.
So like, in your field, when is it most appropriate to like do a crossover design?
Well, I'm not, obviously, you know, in a lot of situations, you will have a carryover of some sort of effect. Well, first of all, if it's something that can have a temporary effect and then wears off, then you could use a crossover design because the fact that you did it before doesn't really affect, you know, what you're doing later, I suppose. It sort of washes out. So that would be one criterion, I guess. I don't know. I've never thought about all the, you know, exactly when it's not something that I've looked at. I mean, I'm sure people have written about crossover designs. I'm not an experimental design expert per se, so I can't give really a complete answer on that. It's not something I've really thought of. But this to me is fascinating. I mean, you know, that you can sort of fool the data into producing something that is very useful by ignoring some information and by sort of, you know, doing that. Okay, yeah.
Would it be correct to say that you're partitioning the data in a different way, or does that phrase partition you not really get at what's going on with
I guess I'm not quite sure. Say what you mean, because, yeah, I'm not sure what you mean by partitioning. It may be.
Like one way of partitioning the data is to take the most specific information you can get. So for each individual person on each individual trial, whether they were cured or treated, so
Right.
it would be like the most fine-grained. And then you could somehow coarse-grained, so where the smallest element of the partition wouldn't be something about just one person and whether they were cured, but whether a pair of people exhibit some disjunctive.
Yeah, I guess so. I think what I didn't say, I was sort of skipping a step in a way. I think, thank you for kind of bringing that up, because, I mean, the other idea is that if you have a large sample, you may want, and a strategy that is done is to create subgroups of people, who, especially if you have only a single variable. It's harder to do if you have multiple variables, but if you had a single variable, you could break people into subgroups, basic strata, if you will. The problem is that usually, you'll get a small number in each stratum, and eventually you'll get it down to where there's nobody except the one person. So this is a way of sort of tricking the data into doing that. Okay.
So the model you were using in that story there was that there's some increment in probability that is always true for each individual.
Yeah,
It's not a logistic. You're not adding you're not adding something on the logistic scale. You're adding on the probability.
right. It's creating a 0-1 variable where before you would have the difference between two outcomes.
So you said that it was exactly equal to the probability of the.
Yes. In other words,
the probability of the treatment establishes. So that's saying that for each individual,
well, that's
no matter what their other factors are, there's a probability increment, not a logistic.
thank you. You're right. It's not exactly that, and thank you for that. That's a good point. What? I'll explain it. Yeah, it's the.
But you're talking about logistic scale, is that what you mean?
It's a logistic. Maybe I don't. I'm getting a little confused on the question, I guess, because it's saying what I would like ideally is to find the probability difference for an individual, but I can't because
So you're saying all individuals.
it's deterministic at that point. I mean, once it's done.
All the individuals have the same probability difference.
But that okay, I know. Let me explain it this way. Okay, can I draw on the blackboard?
Yeah.
Okay, so I create this variable z, okay, and z is equal to 1 if either the treatment is 1 and the control is 1, or the treatment is 0 and the control is 0. In other words, okay, if the treatment is cured in both cases, or, no, I'm sorry, this is not right. Yeah, if under the treatment you would be cured, and under the control you would not be cured, right? Or the other way. Now I'm getting myself confused. Yeah. Okay. If it's treated and cured, or control and not cured, you give it a 1. And otherwise, you give it a 0. Okay? So you create this new variable. It's an indicator of which class it's in. You're collapsing those two classes. So if you have, if you have treatment, control, and then a response or no response, okay, you're collapsing these two cells into an indicator of 1 versus 0. And so this, and as it turns out, it's not hard to show, the probability that z is equal to 1 is equal to 1 plus PA minus PB over 2. And then you can transform that back to get PA minus PB. That's the way it works, really. Okay. So So it's not exactly equal to PA minus PB. It's equal to this. And that's just, it's easy to show that. So it's a way of creating a variable, but this variable depends on your ignoring which treatment it's in. I don't care, I don't want to know that it was a treatment N and R. I want to know that it was just in this category. That's all I want to know.
So you are assuming that PA and PB are the same for all individuals?
No, not at all. In fact, that's the whole idea, is that they may be different for different individuals. But for each individual, this just gives me the probability that for that individual. Okay, and therefore, it should be a way that I can use other variables to predict whether that is high or low for a different individual. Okay? I know, it seems a little bit odd. All of this seems odd, I know. I can send you an article that, sort of does this a little bit more rigorously than what I'm talking about here. Okay, one more, and now I'm going to wade into truly treacherous waters. To me, the two-envelope problem always seemed to me reminiscent of another problem which has been rattling around for about 100 years, okay, in the statistics literature. It's called the Fiducial Argument. Are you familiar with the Fiducial Argument? Glenn's familiar with the Fiducial Argument. Okay. So what is the fiducial argument? Fisher's Fiducial Argument. Well, and to sort of set the tone, this is looked at as sort of one of those, things where people sort of think, well, Fisher was a genius, of course, but and this fiducial thing, he really went off the rails. He just kept insisting that you could do this fiducial probability, but he was really a little cuckoo. So I quote here from a paper in 1992 by someone who's a philosopher at Carnegie Mellon and knows a lot, and he sort of sums up the way people... Seidenfeld, yes. And he said in this article, I hope to show that though it really is untenable as a logical argument, nonetheless it illuminates several key foundational issues for understanding Fisher's disputes over the status of Bayes' theorem, and thereby some of the continuing debates on the differences between so-called orthodox and Bayesian statistics. And he goes on to a very good article talking a lot of detail about how you can give a Bayesian interpretation or not give a Bayesian interpretation, and how different people have tried to reconcile Fisher's idea. Okay, so what is Fisher's idea of argument? And let me give you some quotes from Fisher, which I'm going to talk about, which sound, and this will give you an idea about how his prose can be truly inscrutable, but I think it actually makes sense if you understand what he's talking about, okay? So Fisher said, bear with me here. Somewhere I have it here. Did I take it out? I probably had the foresight to put it on the front and then forgot that I did it, right? Typical. These are Glenn's articles, which I enjoy. Actually, could I get a glass of water? If somebody could get me a glass of water, that would be great. My throat is really getting dry while I sort of hunt through this. Thank you. All right, I've lost it. You know what? I may have to go to the source. Here we go. Go to the source. Since I can't. We'll take a little break for a second while I try to find this. Here it is. Yeah, there you go. Thank you. Should I wait for? Yeah, I'm going to.
Go ahead.
We'll take a little. Shall we continue here?
Yeah.
All right. All right. So Fisher said. Let me give you the little gist of it here. Okay, so in the simplest case, let's suppose you're interested in a normal distribution and you're trying to find out what the mean of the distribution is, okay? And let's suppose, for simplicity, it just has a standard deviation of 1, okay? So it's an unknown mean, but a variance of 1, okay? Now, we know, we would all agree that if you took a sample and calculated the sample mean, right, it would be a normal distribution with mean 0 and variance 1 over n, where n is the sample size, right? Okay, very simple. So Fisher seems to be saying, well, this is what he would call a pivotal quantity. And he said, if you have a pivotal quantity like this, and you know that this is equal to 1, 0 and 1 over n, then, you know, he was sort of saying, well, you could turn that around, and because this is symmetrical, it should still be equal to 1, 0, 1 over n, after you've observed x bar. So that you then have the probability distribution for mu would be normal with mean x bar and variance 1 over n. And people would scratch their head and say, what is he talking about? He's nuts. If you use Bayes' theorem, you know, you can calculate by your prior distribution, you can get, and you know, maybe if you have a flat prior, it's approximately this and blah, blah, blah. But it doesn't make any sense. He can't just reverse it. I mean, we all know that mu, if you're a frequentist, first of all, mu doesn't have a distribution. It's just mu. You pick, you know, it's just there. You know, like if you're looking at a star and you're trying to figure out where it is and you got measurement error around it, it doesn't have a distribution. It has a location, and then there's, you know, you can measure around it. And if you're a Bayesian, you say, well, you know, it has a posterior distribution, but only because you have a prior distribution to start with. So Fisher made this argument, which he didn't like the fiducial probability. It was a fiducial argument, he called it, by which he claimed that you could do this if you were ignorant about the prior distribution. Now, if you had some information about the prior distribution, Fisher said, maybe you'd have enough for a probability distribution, in which case you could use Bayes' argument, Bayes' rule. But if you don't have any information, and if you had a little information about it, you know, then you had to take that information into account. But if you really knew nothing, or thought you knew nothing about the prior value of mu, you had no way to know, then this argument would hold. And people have been trying to figure out what the heck he had in mind.
There's your water.
Sorry?
Your water.
Thank you. Okay. And to make matters worse, Fisher said things like this. He said, probabilities obtained by a fiducial argument are objectively verifiable in exactly the same sense and in exactly the same way as are probabilities assigned in games of chance. He said that. I mean, it's the same. It's not a special probability. He said it's a regular probability. He said, in the Bayesian argument, the observations are used to convert a random variable having a well-defined distribution a priori to a random variable having an equally well-defined distribution a posteriori. By contrast, the fiducial argument uses the observations only to change the logical status of the parameter from one in which nothing is known of it and no probability statement about it can be made to the status of a random variable having a well-defined distribution. And he said that finally, and this one's really a mind bender, he says, it should in general be borne in mind that the population of parametric values having the fiducial distribution inferred from any particular sample does not, of course, concern any population of populations from which that sample might have been in reality chosen at random, for the evidence available concerns one population only and tells us nothing more of any parent population that might lie behind it. What the devil is he talking about, you might say, right? Then he says, being concerned with probability, not with history, the fiducial argument, when available, shows that the information provided by the sample about this one population is logically equivalent to the information which we might alternatively have possessed, given that it had been chosen at random from an aggregate specified by the fiducial distribution. Stuff like this, of course, was totally incomprehensible. But I think I know what he meant now, and I think it has to do with protocols. How about that? I think if he had the idea of a protocol, maybe he would have been able to explain what he was talking about a little bit more clearly, and here's why. I think, yes, I think most of the quotes are from here, yeah. This is a book called Statistical Methods in Scientific Inference, which he published first in 1959, and it's a wonderful book, but you have to be very patient, and you've read it, right, Glenn?
So at the start of this, the investigator has no knowledge at all about the parameter.
Correct.
And it's going to, is it under special circumstances they're going to?
I'm going to explain it. Yeah, I'm going to explain it. All right. So what I think he was talking about was the same kind of sort of weirdness that goes on in the two-envelope game, okay? If you think about it. He's saying basically that if all I know is that this distribution has this, that's all I know. I don't know. I'm trying to measure where a star is, you know, I'm trying to measure its location, and all I know is that I have measurement error around it that has this distribution. That's all I know. And I can observe a bunch of observations so that I get a mean value or on some dimension, okay? He's saying, well, I know before I take any observations that this is what's going to happen. This x bar minus mu follows this distribution, right? And now he's saying, but I now observe x bar. But if it's really true that I have no information about mu, I don't know anything, whatever mu I see is going to be, you know, as equal as any other one in terms of not being surprised, he's saying, well, then it shouldn't matter. X bar is irrelevant to this, so it shouldn't change after I observe x bar. But here's the difference. The difference is before I look at it, this is an objective distribution, right? And after I have observed x bar, this is not an objective distribution anymore. It's a subjective distribution, and it has a logical or rational interpretation. So it's not really the same distribution as this. It just happens to be the same because I don't know any other information. And so he's thinking of it as being the same. And he's saying that, and in fact, if I do this over and over again, it will turn out to be true because in the same way that these other problems are true. He's saying he knows that in this situation mu is already determined, so I don't know what it is, but if I had to make a logical guess at it, it's a good guess to assume that it's within plus or minus, for example, that it would be between two standard deviations of x bar. That's a good guess to make. And that any other, one standard deviation would contain the appropriate percentage and so on. He's saying it's a logical thing to do. That's why I think he was saying, well, it has an objective interpretation. It is a probability. It's a real probability, but it's not a probability. It's a probability in repeated sampling from this distribution. So it's a logical thing to think in this case, even though in this case we already know the answer. Only, you know, it's as if I haven't shown you the answer yet, and you have to guess at what the answer is. So it's a good guess to make, even though in this case we already know. We don't know what it is, but we can know what it is if we look at it. So it's very much like these games, it seems to me. I think that's what Fisher was kind of intuiting in a way, but he didn't have any language in which to express it. And but I think if you follow the logic of saying, well, if I have an event, whatever an event is, or a probability distribution, not just an event, a whole distribution, and that distribution exists beforehand as an objective probability or a physical probability, let's call it, or whatever, and then you have no reason to think that what your information you're getting is relevant to that because you have no prior information about the thing you're interested in, that it's logical and rational to just assume that you can, that will still be true, that distribution will still hold after you make your observations. And I think that's what Fisher, I don't know if that's a good idea or not, but I think that's what he was thinking of when he wrote this, and why it seems so inscrutable, because it's just a very different way of thinking about. It's a different protocol, if you will. You know, his protocol was, was not that there was a prior, but there is no prior. mu is what it is, and it is true objectively that it's just a thing. It exists. It's deterministic, even if you will, but that from a logical standpoint, it's not illogical to assume that I can turn it around and that this is the logical distribution to use.
But you think his protocol was different from Neyman's?
I do. I think Neyman's protocol was that you sort of fix, mu is fixed, and then you sample around mu. If you sample around mu repeatedly, that your confidence interval or whatever would follow from that sampling, that long-term frequency of sampling around the fixed mu. Fisher wanted to know what the probability that was appropriate in this situation as a guide to knowledge about this, even though, and it has a long-run frequency, but in a different sense, I think. That's why he said, he would always say, it's a postulate of ignorance. You have to assume ignorance in order for this to work. If you have any information at all about what the value of mu might be, then this logic doesn't follow through anymore. Because unless you either have a probability distribution beforehand, or you have some partial information that's not enough for a probability, and that would have to be taken into account. So it wouldn't necessarily be logical to have this kind of result.
How does that compare to someone who's a Bayesian, who thinks that the distribution is the maximum entropy distribution, but that represents ignorance?
Wow.
They're different.
I don't know.
Distributions.
I guess I don't know what that you mean by maximum entropy.
The James's.
Yeah, I don't remember the details of that. Maybe. I mean, Fisher said that he was adamantly opposed to an ignorance prior. He did, I don't know. I mean, I don't have a good feeling about, the issues.
He's describing a situation where you start off with ignorance and you end up with a probability distribution.
Yes, and he's saying
you have a kind of after you've gotten some information, so you end up with a posterior distribution.
Yes, exactly.
So there must be a prior that would have given you that posterior thing.
Well, no, because you see, that's where we're talking about that assumes having a probability distribution assumes you have some information to begin with, right? Or not, depending on your point of view. That's why an ignorance prior is sort of a contradiction in terms, according to the way he was thinking about it. Now, I would say also that I'm not sure that a complete ignorance is a meaningful concept either. I don't know if it's possible to have complete
what
ignorance.
I meant is that if he ends up with a distribution, then there will be and he had information, and there will be Bayesian point of view.
Yeah, you
prior distribution, which it is.
Which will produce this, which would produce this.
Right.
That's what Seidenfeld talks a lot about, about people trying to do that. And yes, it's certainly approximately true, I think, that's the case. As a practical matter, I think it is.
So my question was whether that would be the same as the Jane's ignorance.
I don't know. I think I'm not sure there are any practical implications of this, that's sort of not the point here that I'm trying to make, I guess. I mean, I don't know if there are, I don't think Fisher necessarily was right that this could be something that would be a practical use. All I do is, I think what he was saying was not as illogical and crazy as people thought he was, that he did have some insight that he was trying to express. And it was sort of a tragedy throughout his life that he kept trying to hammer away at this and make it work in practical problems and never was able to do that, and that was a big failure for him. And I think he was, but in terms of what he was thinking, I think maybe this sort of helps as to what he was really thinking.
So you kind of brought up the recognizable subsets issue, which you wrote about in that book.
Yes. I'm sorry, I have or have not?
I have not.
Well, not directly. What would you say about that? Yeah, I have.
Well, I have my understanding of it, but that seemed to be the crux of the shortcomings of the argument.
Yeah. Oh, in terms of practical application of it, you're saying?
Well, in terms maybe of the logic as well.
Yeah.
I just recently, I mentioned to you in the hall that I had just recently encountered Bennett's collection of his letters. And it's kind of when you read, is that the first edition of?
Yes, yes, that's the first edition.
19. So he writes in there, he cites Kolmogorov, interestingly enough.
Huh.
He cites a paper that Kolmogorov published in 1942 that's never been translated into English. And somehow, although, like you, I've read the book many times, trying to understand what is Fisher talking about. I sort of never focused on this paper of Kolmogorov's.
Mm-hmm.
I wish and now I wish I could get it. I need to find somebody that is willing to work on this that has better Russian. But in that paper, Kolmogorov brought up this recognizable subsets story. And in terms of betting, I think what he was saying was that does your knowledge of X bar, or the X's, does your knowledge of the observations give you any way to bet against this distribution? So say the distribution is, let's say you do this kind of thing and you're right 95% of the time about your two standard deviations.
Yeah, yeah.
Would the particular X's you see allow you to beat that?
Exactly. Yes, I think that's right.
And he has some, and he says, well, not if you use a sufficient statistic.
Fisher says, yeah, right.
Or if he says, because the sufficient statistic has all the information, maybe it's a multi-parameter problem, then you've got to be sure you're using all the sufficient statistics, maybe you should condition on the ancillaries. But it's clear to me, Fisher, that will take care of the problem. And I shouldn't worry about it.
Yeah, well, I think that's where he got into trouble, yeah.
He got into trouble.
He got into a lot of trouble. Yeah.
So, and, I guess Sandy Zabel and Donald and David Wallace wrote some articles about the controversies and debates that you were referencing.
Yeah.
And they didn't totally bring him down while he was still living, but Kolmogorov's thing does seem to have made it show in that sense. If you want to have those, if you want to expose yourself to that kind of betting, then he doesn't call Fisher as a win. On the other hand, Neyman said, I'm not going to play that game.
Play which game? Sorry.
Of letting somebody bet against me based on the observation. I mean, Neyman said, all I care about is being right 95% of the time.
Right.
The fact that you can look at the observations and find out I'm not so right, that doesn't bother me. I'm just at 95%.
I agree. I don't think this is a practical question. It's something that's always nagged at me because I never understood, and I always thought there was more to it than that. And I think for me the crux of it, in terms of the paradoxical nature of it, is that there's a difference. Like I said at the beginning, there's a difference between prior probability generation and then not knowing the answer, but making a subjective probability judgment about it. And I think that's what Fisher was ultimately talking about.
Well, I agree with you that we should understand that in terms of just what the betting protocols are.
Yeah, in terms of the protocol, what events you're talking about.
What events and what are the rules for the betting?
Yeah, and what are the rules for the betting, right?
And in a sense, I think I guess I'm forced to the conclusion that Neyman came out better than Fisher on this.
It could well be, yeah.
Neyman's betting protocol is not the one we'd like to have. But,
Yeah.
but it's the only one that works.
It's the only one that works.
Well, on this example, you're okay. It's the T. If you do something with a couple of parameters, like the T distribution.
Yeah.
But Fisher was convinced that a fiducial argument with a T distribution would work too.
Yeah, like I say, I don't think as a practical matter, I think that was bad that he went down that road, but he never really articulated his logic clearly.
I thought Bennett's, his letters that Bennett gives are very good because he has some letters there where he.
Well, I'd like to see the book. I mean, yeah.
Yeah, he made some. He had some friends in France, Fréchet and Darmois. And Darmois showed him this French translation, which I have not really seen, but apparently he showed him a French translation of Causalytics. And as he's writing this book, he writes to Darmois and says, "Can you send me that translation?"
Oh.
And then after he writes the book, he writes to somebody else and says, "Well, Kolmogorov may cause some confusion, but I've straightened it out now."
Okay. Oh, God.
I think that book, I think Bennett published those letters after Sandy Zabel and Wallace and all those had written their stuff, and so I don't think maybe they gave it as much attention.
And yeah, I think we can agree that protocols are important, right? Whatever, yeah.
So how would you handle that problem of estimating mu then, in this?
I'm sorry, how would I?
How would you, somebody has to know mu, you have a client, how would you go about estimating mu?
Let me ask you more generally. So
I don't know.
This conviction you have of how you're looking at this came out of your own work, Was that?
I can't, like I said, when I wrote the book, I didn't really have this clear. It was only when I started thinking about some of these other things later on.
So it doesn't come out of your work with your legal work?
No. This stuff. The thing about the control group and the treatment group, yeah, that's actually real. I have an article that talks about using that method, and I've used the method, so that's real. This fiducial stuff is just sort of interesting to me.
I wanted to know what you thought of personalized medicine.
Oh, personalized medicine. Yeah, I'm a big proponent of that. The understanding that it is not easy to do, but I think more and more, we're at a point where it's going to be silly to look at broad averages, and I've written that way, and I believe that. I mean, we'll know enough biologically about individuals that we have to take that information into account. I mean, treatment, a drug is a complex biological intervention, biochemical intervention, right? And it's got to have all kinds of effects on different individuals in different ways. We need to find out about that, and I think drug companies have come around to that belief. Now, I mean, Dave knows more about the practical side of it, I guess, than. Where do you see personalized medicine evolving at this point?
No, I agree completely. Clearly, it's going to be the future. I mean, as people start bringing their genomes around on a chip, your treatment, your risks in life are going to be defined by your genome.
Yeah, I think there was statisticians were sort of brought up feeling like, well, averages are. I had this argument with Don Rubin one time many years ago. I'm sure he's probably changed his opinions now. He was adamant that interactions aren't important. It was only average effects and blah blah blah. But I'm sure he's changed his opinion these days.
Well, surely we're still worried about the reliability of these interactions. They're so complex, and you have so much.
Yes.
It's so many variables. It's really very dangerous.
True. I mean, there are some cases where, you know, a single nucleotide, right, can actually make a difference in certain treatments, and there are examples of that. I mean, you probably can give better examples than I.
I mean, it's called precision medicine. The thing about genomics is how precise, how incredibly precise it is, right? I mean, like Kurt said, one nucleotide change can
Yeah.
disease or health.
Yeah, I mean, that
3.2 billion nuclei. I mean, it's incredible, right? The precision of genes.
Yeah, when you have so many billions of them, you're going to have so few individuals that you observe. And that could be
Some are rare, right?
On a population basis, they'll segregate out, there'll be many instances of somebody who has a BRCA1 gene. That's a
Reputation.
I mean, as a mutation that needs to be addressed or can be treated.
Drug companies could use this information to actually mislead people, right? If they give the test to people that are in a group that they know that it'll do the treatment to people that they think is likely to be effective on, but not report that. So
Well, right,
just
the
report the
indications,
averages.
the indications are tailored to the genome.
Right, but if they don't report that,
Well, that's true.
That's right, Dave. All those evil drug companies that you're working for.
In the past, if you had a client, how would you approach this? This is what.
Oh, I give them fiducial probability any day. I'd refer them to Fisher's book here for the explanation. That's.
so how did Fisher think of the probability distribution that he obtained by the fiducial argument? Do you think of it as an objective probability?
Well, objective only in this strange sense, you know, that he felt it was sort of, like you say, the betting probability was the appropriate thing to do. I think. I don't know of any practical applications where he actually used it in his experimental work or anything.
So he thought of it as a frequency. In the long run, it would.
Yeah, in the long run, that if you bet in accordance with that distribution, you would be right. You would be right the right proportion of the time. I mean, that's the way he felt. Now that it would be logical to do so. I mean, this is a little different, I think, because you may be wrong by ignoring all the prior information, even if it's not a full probability distribution. It might be some qualitative information.
It might be information that you didn't have.
Exactly.
So that it's information that if you had it.
Right. It's really, he's saying if you truly had no information, this is the logical way to infer. But that doesn't mean that the real world would be that way. That's what one of those convoluted quotes that I read for you was trying to say. He was saying, no, this isn't like there's a real population, you know, that I'm talking about. You know, I'm talking about what's appropriate in any particular instance. If I knew nothing in that instance, this would be how I would, you know, how I would operate the bet.
James argues similarly. I don't know enough about it, but I know that Seidenfeld doesn't like James's.
Well, that's beyond. I don't know the.
But James also will say that here's how to get the posterior distribution. You start with when you're in ignorance. You start with this ignorance prior, and you just conditionalize on it.
Yeah, as a practical matter, it may wind up being very, very similar to this. You know, it may make very little practical difference, I think. But I don't know. All right. Any other questions, comments? Yes.
So it's more trying to understand. So in your method for clinical trials.
Yes.
So in this defined as random variable C.
Mm-hmm.
So okay, let me try and describe what I thought I understood.
Okay.
Okay. So you start.
Thank you.
Okay. So you have, say, 1,000 individuals or 1,000,000 individuals.
Yeah.
Okay. So these are actual individuals.
Actual people.
With a name.
Yes.
Separated by each other because they're
Yes.
separate human beings.
Separate human beings. Right.
Now, you come up with a list of parameters, of variables,
Okay.
that can then be used to group this 1 million people into, or this 1,000 people into 100 categories.
Okay.
Like 100 ranges of blood pressure or something.
Yeah, or some combination of variables or whatever, yeah, right.
So then Z compares individuals in that sense. So
Okay, so you still carry out the same, okay, so a person walks in the door in an experiment, right? And you flip a coin to decide which treatment to give them, treatment A or treatment B,
Right.
treatment or control, right? And you then observe their outcome, okay? You record their outcome. Same thing with treatment person B, the next person. So everybody has a treatment and has an outcome. And you then, for each person, translate that into this Z variable. So, depending on which of the categories they're in. So if they land in here or here, you just say, okay, I'm going to count them as being a 1. And if they land in here or here, I'm going to count them as being a 0. So it's as if the experimenter may know what the treatment is, but he doesn't bother to tell the analyst. He's just giving the analyst which category they're in, like, right? And then that becomes the data that you use as your dependent variable, that Z variable, whether it's a 0 or 1. Now, this can be done with continuous variables too, by the way. There's a version of it that works for continuous variables too. But I'm giving the simpler one, which is just the binary outcome, okay? And I'm saying that then you do a regular, you can do a logistic regression, or you can think of it as a classification where you break people up into different categories based on their value of Z now, not, okay?
So when,
And I'm sorry, not based on the value, yeah, Z no, you classify them based on the predictor variables, and then you look to see what their values of Z would be.
so when you say that Z equals 1, if someone was treated and cured,
Yeah.
but also was in the treatment group and cured, but also was in the control group, and either or.
Either or,
Right,
yeah.
I mean, that's
Yeah.
kind of what I'm having trouble with, so.
Well, yeah, so like, look.
We're saying that if there's two distinct people in the same category, one of whom was treated and cured.
Okay, so for every individual, there's let's say a 50%.
If they're in the treatment cure, they're going to have a Z equal 1 if they're cured. If they're in the non-treatment category, they're going to have a Z equal 1 if they're not.
Correct, exactly. So instead of looking at the treatment after you know it, you're stepping back to here and just saying, well, I just want to know, which one of those categories they're in, rather than actually which treatment they were in. I'm going to ignore which treatment they're in, because it's irrelevant. The treatment is really irrelevant to, it's not really relevant to the outcome. I mean, it causes the outcome to be higher or lower, but in terms of understanding the difference between the two, you don't really need to know the treatment. All you need to, because you can use this trick, which basically cancels out the things you don't want and gives you the difference. I mean, that's the way I think about it. If you want, I'll send you the paper. You can look at it. And
What's the name of the paper that this is in?
Sorry? I'll send it to Glenn, and then you can circulate it
Yeah,
around.
we can share.
Okay. So, you have it or not?
No, it's-
I'll send you the paper that came
The
out.
paper, and Eddie can send it to the,
Yeah. Good.
or put it on Sakai.
All right.
Can I ask one more question?
Of course.
It's kind of, well, it's related, I should say, but it's kind of unrelated to any of these details. But just going back to what you said at the very beginning about the probability we used to be on the study of, was it doubt or ambiguity? Or now it's this.
Oh, yes, yes.
Talking about doubt now. Before it was about ambiguity.
Right.
Is there something specific that you pointed to? Was there certain specific references that you know of, or is this just kind of a general assessment?
I have references in the book to a lot of references to the historical literature, but I'm not sure, not about this concept of ambiguity and doubt. That's just sort of a heuristic that I developed as a way to sort of explain the limitation of mathematical probability as being, you know, a proportion on a single dimension. But
But you could give a reference to where Bernoulli was talking about the probabilities of both sides being bigger than one.
yeah. Well, I talk about that at length in that chapter by Bernoulli, and about the way I think he thought about probability. One of the things that he had a very interesting notion of. He talked about pure arguments and mixed arguments. Okay, and to him, a pure argument was an argument that only said whether something was more likely to be true, but didn't say anything about the converse or the other opposite. Whereas a mixed argument told you something about one side, whether it occurred, and also whether it didn't occur. So he distinguished those two types of arguments. And the second type of argument, the mixed argument, is what became our probability. They're all mixed arguments. That's all we have is mixed arguments. You know, it points you either up or down on the spectrum. But he said, but that's only one type of argument. The other type of argument, and he gives examples of that. You know, it's sort of like, he was also a jurist. You know, he knew a lot about the law. He knew a lot about philosophy. And it's sort of like the way people make legal arguments. You know, they sort of talk past each other, right? The plaintiff lawyer gives you all these wonderful arguments. I've dealt a lot with these kind of cases, and it's been fascinating. You can read a case, and you've probably had this experience, Nathan. You know, you read one side of the case, and you say, wow, what a powerful argument. What could they possibly say against that argument? Then you read the other side of the argument, and you say, well, gee, that's a pretty powerful argument, too, and he's saying something completely different. Which one should I believe? And you know, it's amazing. Good lawyers can do that, and then you realize that, of course, their assumptions in the arguments are quite different, and the logic that they're using is different. So they're making very different kinds of arguments. And I think that's the perspective that people used to come from way back when. There is a book that you probably know it. I can't remember the reference of, who talks about probability before, in the Middle Ages and so on. Franklin's book, yeah.
The only one that you know. Yeah. I know that.
Yeah.
But, you know, Edith Scylla has translated Bernoulli's Ars Conjectandi. That's in English now.
Yeah. I refer to that in my book.
The discussion here is about part 4 of that book. So in the first 3 parts of that book are just about games of chance. Then in part 4, he defines probability. As, you know, the ratio of the favorable to the total cases, and then gives his kind of philosophical discussion. And then before he proves the law of large numbers, which is what he's remembered for, there are these sections about how to use arguments to construct probabilities. And that's where Herb was talking about the pure and mixed arguments. In fact, I wrote a paper about this. In '78, I published
yeah, I'm sure you
where I didn't emphasize the examples he gave where both probabilities are bigger than one, but I emphasized where they added to more than one.
Yeah. Well, he has that. Yeah.
Where they added to more than one. He said sometimes they even add more than one, but he put more emphasis on the cases where they added to less than one, which was supportive of the Dempster-Schaefer.
Yes, exactly.
And I emphasized that in the article.
Right.
And he wasn't the only one. There were also other authors who, George Hooper and Lambert gave also. They are examples. Lambert, Hooper came before Bernoulli published. He was English, and Lambert was in the 18th century. He came after. So there were examples of where people were talking about how to construct arguments out of equally likely cases. But the equally likely cases would be about one thing, but when you try to make it an argument, they only are on one side, not on two sides.
Right.
That's the belief function idea in my mind.
That is, yeah. I think you're right, yeah. And it's a good idea, but...
Any other questions?
Okay.
Oh, okay. Thanks a lot.
Thank you.
Yeah.